So Newton has this beginnings of an understanding of the science of mechanics, and the first problem to which he's going to apply it is Kepler's recent results about the motion of the planets around the sun, and Newton has a beautiful chain of logic that we can actually follow that allows him to derive the fundamental physical principle that we suggested might be underlying Kepler's answer. Newton's mechanical understanding tells him that, as we saw, if an object of mass m is moving around in a circle of radius r with uniform speed v, which is a simplified version of the elliptical motion that Kepler actually studied, Newton was doing the general case. We know that moving around in a circle involves a centripetal acceleration towards the center of the circle. So if you see anywhere in the universe an object that is governed by Newton's laws, like everything is, moving around in a circle of radius r with speed v, then there is a force acting on that object and attracting it towards the center of the circle in which it is moving, and the magnitude of that force is the centripetal acceleration that we computed, v squared over r, times the mass of the object, because F equals ma. If you know the acceleration, you can deduce the force. Now, Newton follows, the moon orbits the Earth. The moon is actually moving in a circle about the Earth. So we know that there is a force acting on the moon, which we can compute if we know the radius of the moon's orbit. And thence, because you know how long it takes to go around, you know its velocity. If you knew the mass of the moon, you could compute the force that the Earth applies to the moon in order to keep it moving in a circle. Why do I think the Earth applies it? Well, because it's directed towards the Earth. That's a natural guess. But there's another ingredient here. We know that the Earth attracts everything. Little rubber balls fall onto the Earth because there's this attractive force we call gravity. Apples fall on people's heads, apocryphally. Could it be that the force that keeps the moon in orbit around the Earth is the same as the one that makes tennis balls fall? Well, Newton says, probably. Let's take this seriously. Extrapolating that, let's look at another system. We know Kepler found that the planets orbit the sun in, well, almost perfectly circular orbits at almost uniform speed. Again, that means that acting on each planet is a force directed towards the center of the orbit, in other words, the sun, and we can compute that force. So it makes sense to guess that the sun will be applying this force, and the sun therefore applies a force on all the planets. Then by Newton's third law it would follow that since the sun must be applying force to all the planets, among them the Earth also applies an equal and opposite force to the sun. In other words, if the sun applies a force to the Earth directed towards the sun, it follows that the Earth applies a force to the sun directed back towards the Earth. And now we have lots of cases where the Earth is applying a force to things directed towards the center of the Earth. Perhaps that force too is the same force that makes the moon orbit the Earth and apples fall on people's heads. It all hangs together in a beautiful framework, and we can do the math. So let's start with the idea of something orbiting the sun. So we'll have a planet. We'll call its mass mp. P stands for planet, any planet. And if it orbits the sun at radius r with speed v, then Newton's understanding of mechanics tells us that the force the sun applies to that particular planet is the mass of the planet times v squared over r for that planet. Now, 2 clips ago when we studied Kepler's laws, we found that in fact for any planet that orbits the sun, there is a relation between v and r that is independent of which planet you are considering. For all of the planets, the square of their speed, v squared, is 4 pi squared divided by this interesting constant that I called k for Kepler, times the radius of the planet's orbit. So I can put this expression into that, and I can find F is equal to the mass of the planet times the square of its velocity, 4 pi squared over kr, divided by the radius of its orbit, or rearranging things a moment for a bit, 4 pi squared divided by k times the mass of the planet divided by r squared. Why is this a way to write it? Because the mass of the planet is a property of the planet. R is something that changes between different planets. 4 pi squared over k is the same for all planets. So let's see what we do with this. Well, remember, the idea was that it's all going to hang together, it's all going to be the same force. The sun applies a force given by this expression we found to each planet, and to all the planets it applies the force given by the same constant k. By Newton's third law, each planet applies a force of that magnitude, this precise magnitude, to the sun. Now, universality says that the force that the planet applies to the sun, the force that the sun applies to the planet, should follow from some physical principle that doesn't say, well, the sun is one thing and the planet is another. They're both physical objects. And so symmetry between the two objects tells us that if it's proportional to the mass of the planet, it should be proportional to the mass of the sun. And of course I can do that without any problem. I can say that there is some constant, which I will call g, and if I write that constant such that it's related to k and to the mass of the sun by this relation, then the force expression that I'm writing is equivalent to F is g times the mass of the sun times the mass of the planet divided by r squared. The advantage of this formulation over this one is that here it's clear that there is a symmetry. What the planet does to the sun does to the planet. The force between them is equal in magnitude and opposite in direction, and so there's this symmetric way to write it. But it was clear already that this object here doesn't depend on the planet, so it has to be some property of the sun. The only wild leap here is that the property of the sun it depends on is the same property. The mass and the dependence is the same as the property of the planet upon which it depends, since it determines the force in a symmetric way. And now we can jump to the fact that it's much more universal. Remember, the sun attracts the planets attract the sun. Earth attracts the moon, and the moon pulls on the earth. And in fact, the only way to get a consistent understanding of this is to imagine that the force of gravity is truly universal. Any object applies a force to any other object in the entire universe, and the force is proportional to the mass of the two objects. It's inversely proportional to the square of the distance between them, and there's this universal constant of gravitation that defines what gravitation is and how powerful it is, which very appropriately is given the name Newton's constant. The first measurement we have of Newton's constant is in 1798 by Cavendish, who actually measures the gravitational attraction between two metal balls whose masses he carefully measures separately. So he can actually measure the distance and the masses and find the force and extract a value for g. And g is in the units that are convenient to us, given by this number, 6.67 times 10 to the minus 11 newtons times meters squared per kilogram squared, so that when you multiply it by two masses, kilogram squared, divided by meter squared, you get a force in newtons. So we have this equation, and the way in which it is superior to everything that we have seen so far cannot be overstated. This is a universal statement about anything attracting anything else, and from this follows, for example, Kepler's third law, and of course, by a little more math, all of his other laws describing the motion of the planets, the motion of the moon, and as we shall see, plenty more things. So we found the deep underlying physics that we were looking for, or Newton found it, and we have gotten there. So let's think a little bit about orbits. The moon, as we said, has a force applied to it. The Earth is attracting the moon gravitationally. And one might ask, why does not the moon fall on Earth? And the answer is that the moon is falling on Earth. Remember, moving in a circle is motion with a constant acceleration towards the Earth. Just as my little rubber ball was accelerated down towards Earth, so the moon is accelerated towards Earth with a constant acceleration. To demonstrate this idea, we go back to our pink bowling ball. You'll notice that when I hold it away from me and let it go, the Earth's gravity will always make it fall towards my head, since I'm standing under the suspension point, whatever direction I let it go in. But if I give it an initial velocity that is just right, it will happily circle about my head in a roughly circular orbit while accelerating towards the center at all times. And we also see that by giving it either a larger or smaller initial velocity, I get elongated orbits. They're the analog of elliptical orbits in the case of actually gravitational motion around the Earth or the Sun. We'll do more detailed calculations of all this later, but for the moment we understand that orbiting is just a way of falling without ever hitting the ground, to paraphrase Douglas Adams. What we saw is that uniform circular motion about the center of gravity is a solution to Newton's equations, and if you think back, this would require that I launch the bowling ball with precisely the speed predicted by the Kepler relation and its distance from the center of gravity. What happens if the initial velocity is either too large or too small? Well, as with the bowling ball, you get elongated orbits, and you will not be shocked to learn that in the case of Newtonian gravity, and Newton solved these cases, the result you get is precisely the elliptical orbits with the center of gravity at one focus that Kepler had observed for the motion of the planets around the sun. And so you find that there are all these elliptical orbits, and in fact, there are also open orbits, like this hyperbolic one we see here, which describes the motion of an object that comes in from infinity and recedes off to infinite distance. Of course, if you start along any point of this orbit with the correct velocity, then you will reproduce the latter part of the orbit. So these describe the motions of objects that are not bound to the gravitating blue ball over there, but rather are deflected by it. We'll return to orbits like this in the future. So this is very nice, but it gets even more general than that. Newton's law is universal, so it'll apply to any two objects that are orbiting under the mutual gravity. A little more work shows that we've a little bit been cavalier. We sort of assumed that the sun was stationary and the earth orbiting it, or the earth stationary and the moon orbiting it. You should have known that there's something wrong there, because if the moon is accelerating towards earth due to the earth's gravitational attraction, well, then the earth must be accelerating towards the moon due to the moon's gravitational attraction. Of course, the acceleration of earth is less than that of the moon because the earth is more massive, and this is sort of the situation here. A very massive object and a lighter object are orbiting under the influence of gravity. The cross that's fixed there is the center of mass of the system. Its distance from the center of each object is inversely proportional to the mass of the object, so it's closer to the massive object. It's the point at which these things would balance. But they both orbit each other. The center of each object describes a circle, so they're always on opposite sides of this circle. Taking into account this recoil, you find that in fact the distance between the two, the radius, or if it's an elliptical orbit, the semi-major axis, still satisfies Kepler's law, no matter what the object is. It has nothing to do with the sun. The correct statement, it turns out, when you take into account the motion of the heavy object, is that the constant that relates the square of the period to the cube of the semi-major axis is in fact 4 pi squared over g times the total mass of the system, the sum of the two masses. Now in the case of the sun and the earth, or the earth and the moon, one of them is so much more massive than the other that you can approximate the earth-sun mass as the sun and the earth-moon mass as the earth. This is tantamount to making the approximation that the sun, respectively the earth, does not move and only the lighter object moves. In cases like binary stars, or maybe when you're computing the orbit of Jupiter around the sun, when the masses are closer to each other, then you need to apply this more careful calculation. This will be a very useful result to us, because it means that if we see any two objects orbiting each other in the universe, and we can somehow find the period in the semi-major axis, we can compute their mass. And if you look in your texts and you find the mass of planets and galaxies and stars, you might ask yourself, how did somebody compute the mass of a distant star, or for that matter, Jupiter? And the answer is, you find something orbiting it and you apply Kepler's relation. And so this will be an extremely powerful tool as we go on. All this theory, let's do an example. And let's consider the International Space Station. The International Space Station orbits at an altitude above the ground of about 370 kilometers. Adding that to the Earth's radius, we find that the radius of its orbit about the center of the Earth is about 6,700 kilometers. And so we can find its period. Its period is given by our relation p squared equals k times r cubed. And plugging in our value for k, we find 4 pi squared over g m Earth times r cubed. Notice that I've neglected the mass of the International Space Station relative to the mass of the Earth, which is a very fair approximation. And when we plug in the numbers, we find that the period is Taking the square root, we get this expression, extracting the 2 pi, plugging in all the numbers, Newton's constant, the mass of the Earth, and remembering to convert the radius of the Earth to meters to match the units in which we wrote Newton's constant, we find a period of 5,500 seconds, or about 91 minutes, the International Space Station and all low Earth satellites, or nothing was special to the International Space Station, anything that orbits at about the Earth's surface, orbits the Earth every 90 minutes. When you see satellites crossing the heavens, they all appear to move with a uniform angular velocity. This is the reason Kepler is telling us that they all orbit once every hour and a half. I hope that you're as impressed as I am with what we've managed to achieve by following Newton. We have found the fundamental universal laws that underlay the regularities of Kepler's laws. In Newton's time, what helped people appreciate this was the understanding by Edmund Halley that comets, these weird objects that would appear in the sky, move along the celestial sphere in some random direction, then disappear again, were actually objects that were in highly elliptical, highly eccentric elliptical orbits about the sun, spent most of their time far from the sun and invisible, and were visible to us when they came near. He used data that had been collected to predict the appearance in 1705 of a particular comet in the sky over London to within a day, and luckily he got it just right. People stepped out on the day that Halley's Comet, as it has come to be called, showed up, and the validity and the importance of Newton's result was understood. Here's a beautiful image of the passage of Comet Halley in 1986. It has a 75-year period as it orbits the sun. Try to figure out its semi-major axis. Gravity works. We'll come back and do some more details. We have some more things to learn about how much information we can get out of Newton's theory. We'll turn to that in the next clip.